Good morning, everyone. Welcome back. Last time we laid the foundation, we talked about the general characteristics of pipe flow. We learned that when a fluid enters a pipe, it goes through an entrance region before setting into what we called the fully developed flow. In that region, the velocity profile stops changing. It's the same at any cross section. We also introduced the fundamental distinction between laminar and turbulent flow governed by the Reynolds number. And we saw that in any fully developed flow, there is a simple, elegant balance. The pressure forces pushing the fluid are exactly balanced by the viscous shear forces resisting it. No acceleration, just a force balance. Today, we are going to cash in those concepts. We are going to take that force balance, combine it with what we know about how fluid behave, and exactly derive the equations that govern fully developed laminar flow. This is one of the few times in fluid mechanics that where we can get an exact solution from the theory alone. It's beautiful, it's powerful, and it's the foundation for understanding everything that comes after, including the more complex world of turbulent flow. So let us start the topic fully developed laminar flow. Now, the textbook of Munson gives us three ways to derive this, but we are going to start it with the most intuitive one, applying F is equal to ma Newton's second law directly to a fluid element. So let us visualize this. Imagine a horizontal pipe, and inside it, picture a small cylindrical chunk of fluid. It's centered right on the pipe's axis. It has a length, let's call it L, and a radius R. This is our free body diagram as shown over here. Now, what forces are acting on this cylinder in the direction of the flow, which is the x direction? There are namely three forces. One is the pressure force on the left hand, the second one is the pressure force on the right hand, and the third is the shear force on the lateral surface. Now, let us briefly explain all these three forces. The first one, pressure force on the left hand. The pressure at the left face, P1, pushes it to the right. That force is P1 times the area, which can be written as P1 multiplied by pi r square. The second one is the pressure force on the right hand. The pressure at the right face P2 pushes it to the left. But since pressure drops in the direction of the flow, P2 is less than P1. Let us call the difference P1 minus P2 as delta P. So the force on the right end pushing left is given by P1 minus delta P multiplied by pi r square. Then the third force, shear force on the lateral surface, the fluid around our body is sticky. It exerts a viscous shear stress tau on the side of our cylinder, pulling it backwards to the left. This shear stress acts over the entire lateral surface area, which is the circumference times the length given by 2 pi RL. So the total shear force is tau times 2 pi RL. Now here is the key assumption for a fully developed flow, that the fluid is not accelerating. It is moving at a constant velocity. This is the point made in the following derivations, so which also dictates that the sum of the forces in the x direction must equal to zero, which can be seen from these equations, that the forces on the right minus the forces on the left must equal to zero. P1 times pi r square minus P1 minus delta P pi r square minus tau 2 pi rl must equal to zero. Notice the minus sign in front of the shear force because it's acting to the left, which gives us that we cannot cancel pi and 1r from both sides and solve for the shear stress, and we can write the final equation as delta P over L must equal to 2 tau divided by R. So this is the fundamental balance equation. It tells us that the pressure drop per unit length delta P over L is directly proportional to the shear stress divided by the radius R. Now think about what this implies. The left-hand side delta P over L is a constant for a given pipe and flow rate. It does not depend upon the radius r, so the right side that 2 tau over r must also be constant. This means that tau itself must be proportional to the radius r. In other words, the shear stress varies linearly from the center line to the wall. At the center line, where radius is equal to 0, the shear stress is 0. Makes sense, right? The fluid at the very center is not being sheared directly. At the wall, where radius is the half of the diameter, the shear stress is at its maximum. So we call this wall shear stress as tau subscript W. So we can write this linear relationship as tau is equal to 2 tau W multiplied by the radius divided by the diameter. So this is a powerful result. And here is the critical point that this linear stress distribution is true for both laminar and turbulent flows. It comes purely from the force balance independent of the flow type. So we will come back to this later. Now, here is where the laminar and turbulent flows go their separate ways. This is the second way to derive the equation to get from the shear stress to velocity. We need to know how the fluid shears. For a Newtonian fluid in laminar flow, we have a simple experimentally verified law that the shear stress is proportional to the velocity gradient, which is given by this equation. Tau is equal to minus mu du by d of r. The negative sign is just a mathematical convenience because velocity decreases as r increases. Du by d of r is negative, and we want tau to be a positive number. So mu, of course, is the dynamic viscosity. Now, the magic happens. We have two expressions for tau, one from the force balance and one from the fluid definition. Let us set them equal using the journal form from previously derived equation. Tau is equal to delta p over 2L multiplied by the radius r. So we can get a particular equation, rearranging it to isolate the du by d of r term, we can write the subsequent equation as shown over here. So this is a simple differential equation. It says that the slope of the velocity profile is a straight line. To find the velocity itself, u is a function of the radius, so we integrate with respect to the radius r as integration with respect to the du, it must be equal to minus delta p over 2 mu l, and integrated over the radius d of r. So it gives us a constant integration constant c1. To find it, we need a boundary condition. So what is it? The no slip condition at the pipe wall. The fluid sticks to the wall, so at radius is equal to d by 2, the velocity is equal to 0. So let us plug that in, and we can easily substitute C1 back into the equation for the velocity u as a function of r. We can factor out the common terms to get the classic parabolic velocity profile as listed over here, which is the u as a function of r is equal to delta p d square over 16 mu l bracket 1 minus 2 r over 2 whole square bracket close. So as and look at the very that first term. It's the velocity at the center line where r is equal to 0. So let us call that the center line velocity vc. Vc must be equal to delta p d square over 16 mu l. So putting that back in, we can get the simplified form. Velocity as a function of radius r equals to vc 1 minus 2r divided by 2 square. So this is it. This is the exact velocity profile for fully developed laminar flow in a pipe. It's a paraboloid. It's zero at the walls, maximum at the center, and beautifully smooth. This flow is so important, it has a name, Hagen-Poiseuille flow. after the two scientists who first described it experimentally in the 1830s and 40s. Now, this profile is very great, but engineers care about practical things. How much fluid is moving and what pressure drop does it require to integrate this velocity profile over the entire pipe cross section. So think of the pipe as a bunch of tiny rings. Each ring at radius r has an area dA equals to 2 pi r times dr, and the fluid in that ring is moving at a velocity u bracket r, u as a function of r. So the flow rate through that ring is ur multiplied by the dA. So we sum up all the rings from the center, which is at radius r is equal to 0 to the wall. R is equal to capital R, where R is equal to d by 2. This is shown in the figure also. So if we solve through the integration, as we can see on this particular slide, so we can get a very good result. Now the average velocity v is simply q divided by the cross-sectional area, and we can simplify this as v is equal to vc over 2. So this is the key takeaway. In laminar pipe flow, the average velocity is exactly one half the maximum centerline velocity. Not one quarter, not something else, exactly one half. Now, we can substitute back our expression for Vc in terms of the pressure drop. Remember Vc from the previous derivation that Vc is equals to delta P d square over 16 mu L. So we can get the velocity final form uh, as delta P d square by 32 mu L. And if we want the flow rate in terms of the pressure drop, we can multiply it by the area. Area is equal to pi d square divided by 4 to get the famous Poiseuille's law, which is represented over here as Q is equal to pi d4 raised to the power 4 times delta P divided by 128 mu L. Now look at this equation. It is a thing of beauty and it tells us everything that Q is directly proportional to the delta P, doubles the pressure, double the flow. Q is inversely proportional to the viscosity and the length L. More viscous fluid or a longer pipe means less flow. And thirdly, it also tells that Q is proportional to the D4, D raised to the power 4. So this is the killer. If you double the pipe diameter, the flow rate increases by a factor of 2 raised to the power 4 is equal to 16 times. So this shows the incredibly sensitivity of the pipe flow to the diameter. A small error in measuring d, the diameter, leads to a huge error in calculating the volume flow rate q. Now coming towards the non-horizontal pipes and the friction factor, our derivation assumed a horizontal pipe earlier. But what if the pipe is on a hill? This topic covers with this particular figure as displayed. Gravity now plays a role. If the pipe is at an angle theta, the weight of the fluid has a component along the pipe axis. If you go through the force balance again, you will find that you can account for this simply by replacing the pressure drop delta P with an effective driving force, which is delta P minus gamma L sine theta, where gamma is the specific weight. If the flow is downhill, which means the theta is negative, the gravity helps and you need a smaller pressure drop. But if it is uphill, the gravity fights you and you need a larger pressure drop. This leads to the more general forms, but the core physics is the same. Now, there is one more way to look at this, and that it is incredibly useful for engineering. Let us rewrite our pressure drop equation in a dimensionless form. We have delta P equals to 32 mu L divided by mu LV divided by d square. Let us divide both sides by the dynamic pressure term, which is one half rho v square. So why we are doing this? Because that dynamic pressure is a measure of flow's kinetic energy. Delta P over half rho V square would give us the final form as represented over here as 64 over Reynolds number L over D. We can rearrange this to define a new incredible important parameter called as a friction factor F. So it is being defined by this equation, but for now, think of it as a dimensionless way to express the pressure drop. So delta P must be equal to FL over D, V rho V square over 2. By comparing this with our derived equation, we see that for fully developed laminar flow, the friction factor is simply F is equal to 64 over Reynolds number. So this is a clean, simple, and universal result. The friction factor for laminar flow is only a function of the Reynolds number. It does not depend on anything else, not even the pipe's roughness. So we will see a stark contrast when we get to the turbulent flows. Now, moving on to energy considerations, finally, let's tie this back to energy. Remember the energy equation from the earlier concepts. It included a term for head loss, which we used to represent as HL. For fully developed flow between 2 points, the velocity profile does not change. So the kinetic energy correction factors alpha 1 and alpha 2 are equal. That means that the kinetic energy term cancels out. The energy equation simplifies dramatically to the following equation. So, what does this say? It says that the head loss HL is exactly equal to the drop in the piezometric head. That's the pressure head, elevation head. The energy dissipated by viscosity is supplied by the work done by the pressure and the gravity forces. So it's a perfect energy balance. And using our earlier relationships, we can connect this head loss directly to the wall shear stress, leading to the following equation as HL equals to 4L tau W divided by gamma D. So the head loss is directly proportional to the wall shear stress. The harder the fluid has to work to overcome viscous resistance at the wall, the more energy is lost. Now, let us summarize what we have studied in this particular lecture up till now. We have we started with a simple force balance on a fluid element. We combined it with Newton's law of viscosity for a laminar flow. We integrated to find the parabolic velocity profile and the hallmark of laminar pipe flow. From that, we derived Poiseuille's law, which tells us that the flow rate is proportional to the pressure drop and, most importantly, to the fourth power of the diameter. We also expressed this in a compact dimensionless form with the friction factor as F is equal to 64 over Reynolds number. So this is the complete, exact and beautiful solution. It is a masterpiece of theoretical fluid mechanics. But as we noted last time, the most real world flows are turbulent. And the turbulent flow is not this neat and tidy. Next time, when we will be discussing the next section, the fully developed turbulent flow, we will be exploring the chaotic world of fully developed turbulent flows. We will see how the velocity profile changes, how the shear stress is more complex, and why the friction factor is no longer a simple function of just Reynolds number. So for now, make sure you understand how we got from that force balance to Poiseuille's law. It's the core of this section. So see you next time.